Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the curious and sometimes contradictory world of time and the even stranger discoveries that quantum physics has added to the mix. But before you settle in and get cozy, I'd love it if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Time feels like the most familiar thing in the world. You wake up to it every morning when the alarm clock sounds. You feel its passage in the slow steam rising from your cup of tea, in the way shadows lengthen toward evening, in the quiet change of seasons. It marks birthdays and anniversaries, deadlines and long-awaited holidays. You can measure it with a stopwatch or lose it completely in a good conversation. For most of us, it's a steady, invisible companion, always there, moving forward in the same way, no matter what we are doing. It seems so simple, so dependable, that it's easy to forget to ask what it really is. And then, science comes along, taps you on the shoulder and says, it's not that simple. If you take a clock into space, moving at high speed, it will tick more slowly than the one you left at home. If you place another clock on the floor and one on a high shelf, the one closer to the ground, closer to the pull of Earth's gravity, will run just a fraction slower. These aren't quirks of broken watches. They are real effects we can measure with extraordinary precision, effects predicted by Einstein's theories of relativity. In this picture, time is not an unchanging backdrop, but a flexible thing, a soft fabric woven together with space itself, bending and stretching with motion and gravity. Yet if you ask a quantum physicist, someone who studies the strange subatomic rules that govern the smallest parts of reality, you'll hear a very different story. In quantum mechanics, time isn't flexible at all. It doesn't bend or stretch. It marches forward at the same steady pace everywhere, like the beat of a perfect invisible metronome. This isn't a matter of disagreement over a small detail. It's a fundamental mismatch in the way two great theories, relativity and quantum mechanics, see the world. Each has passed every experimental test thrown at it. Each explains its own realm of reality, beautifully. And yet, when they meet at the edges, in places where both the immense gravity of relativity and the delicate structure of the quantum world are important, their versions of time cannot be reconciled. It's a little like asking two trusted friends about the same person and receiving two completely different descriptions. One insists they are restless, always changing, shaped by the forces around them. The other swears they are steady, predictable, and constant. Neither is lying. They are simply speaking from different experiences. But here, the person they're describing is the very thing that makes experience possible. Time itself. You might think that the solution is simply to look harder, to find the one correct version of time. But there is another possibility, one that has been gaining quiet traction in the physics community, and which has a way of gently unsettling the assumptions we carry. Perhaps time, as we know it, doesn't exist in the way we imagine. Perhaps it's not a basic ingredient of the universe at all, but something that emerges like the smell of bread emerging from the baking, only when certain conditions are met. In this view, time could be the product of relationships between things, rather than a stage they all move across. Instead of imagining time as a single river flowing from past to future, always in the same direction and at the same speed, we might think of it as countless little streams, each shaped by the terrain it runs through, sometimes moving at different speeds, sometimes drying up entirely, and sometimes, in the strange, delicate conditions of the quantum world, Those streams may not exist at all until we dip our hands into them. It's not an idea that fits easily with everyday life, and that's part of why it feels so strange to entertain. You can't simply tell your boss that time has stopped because the relational correlations in your kitchen weren't strong enough to produce it. But in the quiet reaches of theory, supported by carefully crafted experiments, physicists have begun to explore models where the universe as a whole might be entirely timeless, and yet, from the inside, from our perspective as participants within it, time flows exactly as we expect. This is where our journey tonight will lead, through the landscapes of relativity and quantum mechanics, past the gentle bends of gravitational time dilation, into the microscopic thickets of quantum entanglement, and toward the deep, still pools where causality itself becomes uncertain. We'll meet ideas that feel like riddles, experiments that behave like stories, and possibilities that ask us to rethink the very rhythm of our days. And as we travel, remember, there's no need to catch every detail. Let the ideas pass like clouds, lingering if they catch your interest, drifting by if they don't. After all, time, whatever it is, will keep flowing, even if it turns out to be nothing, more than the way we notice change. If you could step outside of your daily life for a moment, beyond the walls of your home, past the sky above your head, into the quiet dark where the stars seem close enough to touch, you might notice that time feels different there, not because the ticking of your wristwatch has changed, or because your heartbeat has slowed, but because of something far deeper, built into the very geometry of the universe. This was one of Albert Einstein's most surprising gifts to the world, the realization that time is not an absolute unchanging thing. In his special theory of relativity, he showed that time runs at different speeds, depending on how fast you're moving. The faster you go, the slower time flows for you compared to someone standing still. It isn't a matter of perception. It's a real physical effect, so real that it can be measured. You might imagine two identical twins, one who stays on Earth and one who boards a spaceship that travels near the speed of light. When the travelling twin returns, they will have aged less than the one who stayed behind. The difference may be tiny for ordinary speeds, but for velocities close to light, the effect becomes dramatic. This is time dilation, the stretching of time caused by motion. Einstein didn't stop there. In his general theory of relativity, he found another cause for time dilation: gravity. Imagine the surface of the Earth as a gentle curve in the fabric of space and time. The closer you are to the source of gravity, in this case the centre of the Earth, the more the curve deepens and the more time slows. A clock placed at sea level ticks a little more slowly than one at the top of a mountain. The difference is almost unimaginably small in our daily lives, but it's enough to matter for things like the GPS satellites orbiting above us. Their clocks, high above Earth's surface, tick slightly faster because they are farther from the pull of gravity. Engineers have to account for this, adjusting the system so that the signals guiding you to the nearest cafe arrive in step with your own sense of time. It's tempting to think of time as a long straight hallway, each step evenly spaced from the next. But relativity tells us it's more like a soft, flexible carpet, stretching or compressing depending on where you step and how quickly you move. If you could lay out the entire universe as a single piece of fabric, it would ripple and fold around stars, planets, and black holes. Every bend in that fabric would not only change the paths of objects moving through space, but also alter the rhythm of their passage through time. We tend to talk about slowing time, as if it were some exotic science fiction trick, but in truth, we're all experiencing tiny variations every day. When you climb a hill, your time runs just a fraction faster than it does for someone at the bottom. The effect is so small that without the precision of atomic clocks, we would never notice. But the mathematics that describes it is as exact and unyielding as the ticking of any clock. One of the most beautiful things about relativity is how it unites space and time into a single concept: space-time. Instead of thinking of space as one thing and time as another, Relativity says they are woven together, like threads in a single piece of cloth. Pull or stretch one, and the other changes too. This is why gravity can bend light. Light moves through space-time, and when space-time curves, light's path follows that curve. This is also why gravity can change the pace of time. When the fabric curves, the clock sewn into it runs differently. The closer you look, the more you realize that time in relativity is not the universal heartbeat we once imagined. There is no master clock ticking away somewhere in the universe that all events obey. Instead, each path through space-time has its own measure of time, its own proper time, as physicists call it. Your proper time is different from that of a satellite or an astronaut, or even your friend standing a few meters away, though the difference is too small for you to feel. For most of human history, this idea would have been unimaginable. Time seemed to flow with the same steady beat for everyone, everywhere. The sun rose and set together for all. A minute was a minute, whether you were in a valley or on a mountaintop. Einstein's insight was that the world is far stranger than it appears, and that time is not a background against which events unfold, but something shaped by those events, just as they are shaped by it. In a way, this view of time makes the universe feel more alive. If time can stretch and contract, it is not rigid but responsive. It listens to motion, to gravity, to the deep architecture of space-time. It is a partner in the dance, not just the music in the background. And yet, as flexible as relativity's time is, it still clashes with the quantum world's version, that steady, absolute metronome that ticks the same for all. To reconcile the two, we will have to go deeper, to look at the smaller scales of reality, where particles can be entangled, where cause and effect can blur, and where the familiar flow of time may not exist at all, until the right conditions bring it into being. But before we wander into that territory, it's worth lingering here for just a moment longer, imagining the soft fabric of space-time, feeling the quiet pull of gravity on our clocks, and realizing that even now, as you listen to these words, your time and mine are already slightly, invisibly out of step. If Einstein's relativity paints time as a soft, flexible fabric, quantum mechanics sketches it as something far more rigid, a straight, unyielding ruler laid alongside the universe, measuring every moment with identical, unwavering marks. In the quantum world, time does not stretch when you move quickly, or slow down under the pull of gravity. Instead, it marches forward with the same steady rhythm, as if kept by a perfect metronome that never misses a beat. This isn't because quantum mechanics ignores motion or gravity. It's because, in the mathematical heart of quantum theory, time is simply assumed to be absolute. When you write down the Schrödinger equation, the rulebook that tells a quantum system how to evolve, time appears as a single parameter, the same everywhere. No matter where the particles are, no matter how far apart or how differently they move, the tick in the equation is uniform. There's no warping, no slowing, no stretching. Just one consistent background tempo against which the dance of particles plays out. You might imagine a vast concert hall filled with countless musicians, each playing their own melody, but all keeping perfect time with the same conductor's baton. The melodies can rise and fall, grow complex or simple, but the beat beneath them never wavers. This is how quantum mechanics treats time, as the silent, invisible pulse that drives all motion, unaffected by the players themselves. From a practical standpoint, this works beautifully. Quantum theory has predicted everything from the behavior of atoms to the properties of semiconductors with astonishing accuracy. It's the reason lasers work, why transistors exist, and why we can perform delicate experiments with individual particles of light and matter. And yet, for all its power, quantum theory doesn't try to explain where time comes from or whether it has a shape. It simply assumes it's there, fixed and universal. This creates a quiet but profound tension. Relativity says there is no single, universal clock. Each path through space-time has its own time. Quantum mechanics says there is one clock for everyone and everything. In everyday life, we never notice this mismatch because the effects relativity describes are tiny at small scales, and the assumptions of quantum theory work perfectly in most laboratory settings. But in certain extreme situations, near a black hole's edge, in the first fractions of a second after the Big Bang, or inside the dense, delicate heart of a neutron star, both theories must apply at once. And when we try to let them speak to each other, their stories about time collide. This collision isn't just a mathematical inconvenience, it points to something deeper, something unfinished in our understanding of the universe. If two of our most successful theories can't agree on something as fundamental as the nature of time, then perhaps time itself is not fundamental. Maybe it's like the surface of the ocean, something we see and feel, but which only exists because of deeper movements beneath. It's worth pausing here to notice how odd this really is. We're so used to thinking of time as the stage on which events happen that it's hard to imagine the stage itself being built out of those events. Yet, in the tension between relativity's flexible time and quantum mechanics' steady beat, we see the first hints that this might be true. Perhaps time is not the same for everyone because it is created differently in different circumstances, or perhaps the same time in quantum mechanics is an illusion, a simplification we've been able to get away with so far. One of the strange side effects of quantum mechanics' fixed time is that it seems to resist the idea of before and after being relative. In relativity, the order of events can change for different observers moving in different ways. What looks like first this, then that, for you may look like first that, then this for someone else. In quantum theory's math, the sequence of events is fixed by that universal ticking clock. The two views are not just different shades of the same idea, they are speaking about fundamentally different realities, and yet both of them work. Both of them have been tested to limits that seemed impossible a century ago. We have measured time dilation in aircraft, satellites, and particles moving close to light speed, and it matches relativity perfectly. We have tested quantum predictions in laboratories around the world, with results so consistent it's almost unsettling, and they match quantum mechanics perfectly. The universe, somehow, manages to follow both sets of rules until we look too closely, and the mismatch becomes unavoidable. Physicists have spent decades trying to bridge the gap, searching for a deeper theory that would contain both relativity's flexibility and quantum mechanics' precision. The search has led to ideas like quantum gravity, looped space-time, and even the possibility that time itself emerges from something more fundamental, not a clock at all, but patterns of connection, correlation, and information. We'll explore that in the next part of our journey, but for now, it's enough to feel the strangeness of where we are, standing between two visions of reality, both true in their own ways, yet unable to meet without changing the meaning of time itself. As you think about this, about the idea that the ticking you feel in your own life might be just one of many possible rhythms the universe can play, you might imagine that vast concert hall again. You can picture the conductor's baton marking each moment with flawless precision and the musicians following without fail. Now imagine the lights dimming and another figure stepping onto the stage, whispering to a few of the players to slow down, to stretch their notes, to let the melody breathe. The two rhythms begin to weave together, not in harmony yet, but in something more complicated, more mysterious, and perhaps more beautiful than either one alone. This is the space between relativity and quantum mechanics, the place where the steady beat and the flexible flow first meet. Imagine pressing pause on the entire universe, not just the people and the planets, not just the weather or the turning of the earth, but every atom, every particle, every flicker of light brought to a complete and perfect stop. In this imagined freeze frame, galaxies hang like jewels in the dark, their stars suspended mid-glow. A bird in flight is caught forever with wings half folded. You yourself are still, your thoughts held in the same stillness as the air around you. From the outside, nothing moves, nothing changes, nothing flows. It is a picture so perfect that it would never age. Now, here's the strange part, inside that picture, the story might still be unfolding. The bird could still beat its wings. Your mind could still wander, recalling old memories or imagining new possibilities. Conversations could still be exchanged, music still played, moments still felt, all without anything in the picture as a whole moving forward. This is the heart of an idea proposed in 1983 by two physicists, Don Page and William Wootters. They wondered if time itself could be like this. Not a single, universal current that sweeps all of reality along, but something that emerges from the relationships between parts of the universe. In their picture, the universe as a whole doesn't have a clock ticking away in the background. Instead, time is something you only notice when you compare one part of the universe, your clock, to another part, the system you're watching. If the universe were truly static, with all its parts in one unchanging state, there would be no time, no change, no story. But if you split it into pieces and look at how those pieces are connected, how they're correlated, you could find patterns that act just like the ticking of a clock. Those patterns, Page and Wootters suggested, might be all we need to create the experience of time. It's a radical thought because it flips the usual order of things. We tend to believe that time exists first, and events happen within it. They were suggesting that events, or more precisely the relationships between them, come first, and that time is just the name we give to the way those relationships unfold. You can think of it like a duet between two musicians. If you listen to just one of them in isolation, you might not hear a rhythm at all. But if you listen to them together, the way they align and shift, the rhythm becomes clear. The beat isn't being kept by some separate drum off stage. It's being created in real time by the interplay of the two players. In the same way, Page and Wootters imagined that a clock and a system could create time between them, even if the universe as a whole had no master clock-keeping score. This leads to a strange but beautiful consequence. From the outside, the universe could look timeless, frozen. From the inside, to those of us who are part of its fabric, time would seem to flow naturally. The illusion would be perfect, not because it's a trick, but because for those on the inside, it would be real. There would be no way to tell the difference between true time and time made from correlations, because for the observer, the two are indistinguishable. Page and Wootters developed this idea mathematically, using the tools of quantum mechanics. They showed that if the universe is in a very special kind of quantum state, one where all its parts are entangled in just the right way, then an internal observer could measure change without any external time passing at all. What's more, the way we think of now would depend entirely on the observer's role in this network of connections. There would be no universal now shared by everyone, only the now you carry with you, tied to the correlations you can see. It's a quiet revolution, because it doesn't declare time an illusion outright. It doesn't tear down the clocks or deny our experience of moments passing. Instead, it whispers that perhaps our clocks are telling a story that exists only because of the relationships we're part of, and that if those relationships were somehow broken or rearranged, the story might stop, even though the universe itself hadn't changed in any global sense. For a long time, this idea was mostly philosophical. It was beautiful, and it fit neatly into certain interpretations of quantum theory, but it seemed impossible to test. After all, how could you step outside the universe to see whether it was truly timeless? How could you look at both the whole frozen picture and the moving parts within it at the same time? And yet, decades later, physicists would find a way to bring the essence of the idea into the lab, not by freezing the entire universe, of course, but by creating a tiny, self-contained world of their own. In this miniature universe, made of just two particles of light, they would try to see if time could emerge in exactly the way Page and Wootters had imagined. That experiment, involving two entangled photons, one acting as the clock and the other as the system, would not only bring the thought experiment to life, but also hint that our own experience of time might be far more fragile and far more relational than we ever guessed. We'll step into that experiment next, but for now, it's enough to let the image settle in your mind. The universe as a perfect still frame, and yet, within it, all the quiet motion that makes a life. For 30 years after Page and Wootters published their idea, it remained mostly in the realm of theory, something that lived on paper, beautiful but unreachable. You could imagine the universe as a still photograph. Imagine time appearing only in the interplay between parts, but imagining is one thing, and proving it is another. Testing the idea seemed as impossible as leaving your own dream to check whether the world outside was still asleep. Then, in 2013, a group of researchers in Italy decided to try. They couldn't freeze the entire universe, of course, but they could create a tiny, self-contained world of their own. Instead of planets and stars, their universe would be made of just two particles of light, photons. In this miniature stage, they could control almost every aspect of the performance, and in doing so, they could ask, if time can emerge from the relationship between a clock and a system, could we see that happen here? The experiment was elegant in its simplicity. One photon would play the role of the clock. The other would be the system whose changes we wanted to observe. But the two wouldn't just sit in the same space minding their own business. They would be entangled, linked together in such a way that the state of one instantly influenced the other, no matter the distance between them. Entanglement is one of the stranger features of quantum mechanics. It is as if you had two coins that, when flipped far apart, always landed in matching ways, both heads or both tails, without any signal passing between them. In the Page-Wooters view, this entanglement is exactly what allows time to appear for an internal observer. If the clock photon and the system photon are entangled, then the state of one can be used to tell the time for the other. Changes in the system photon can be measured relative to the ticking of the clock photon. But from the perspective of an external observer, someone looking at both photons at once, nothing changes at all. The entire two-photon system remains in the same overall quantum state, perfectly still. The researchers designed their setup so they could look at the experiment from both perspectives. When they examined just the system photon, using the clock photon to mark time, they saw change, evolution, as if time were flowing naturally inside this tiny universe. But when they stepped back and looked at the entangled pair as a whole, they found no change at all. From the outside, the system was frozen. From the inside, time was alive and moving. It was a moment that blurred the line between thought experiment and reality. Here, in a carefully controlled laboratory, the essence of the Page-Wooters idea had taken physical form. Time, in this case, was not a universal backdrop. It was an emergent property of correlation, born from the entanglement between two tiny particles of light. Of course, no one is claiming that two photons in a lab capture the full complexity of the universe, but the experiment showed that the concept could work, at least in a small, idealized system. It gave physicists something to point to, a tangible example of how a timeless whole could still contain the experience of time within it. And perhaps most importantly, it suggested that our own flow of moments might not require a cosmic master clock at all. It could be the result of the relationships that bind the universe's pieces together, the shared rhythms between its countless clocks and systems. You can think of it like reading a book with a friend. If you both have the same edition, you can keep track of where the other is by comparing page numbers. You don't need to look at the clock on the wall to know if your friend is ahead of you in the story. You just need to compare your positions. That's what the photons were doing, measuring progress not against an external, universal standard, but against each other. And just as in a good book, time inside the story can feel very different from time outside it. From the inside, the characters live and act and change. From the outside, the book is already complete, the entire story fixed from the first page to the last. Both perspectives are true, depending on where you stand. This experiment didn't solve the grand puzzle of reconciling relativity and quantum mechanics, but it nudged the conversation in a new direction. It made the abstract seem a little less untouchable, a little closer to home, and it hinted that time, the thing we treat as so solid and absolute, might be more fragile, more dependent on context than we ever suspected. It also leaves an unsettling question hanging in the air. If time depends on correlations, what happens when those correlations fade? If the universe's entanglement ever unraveled, or reached a state where everything was perfectly correlated with everything else, would time as we know it simply stop? That's not a question we can answer tonight, but it's one to keep in the background as we move forward, because it will return later in our journey. For now, it's enough to remember the image: two particles of light, locked together in a silent duet, creating time for each other, even as they remain motionless to the outside world. A tiny laboratory echo of the possibility that the flow of moments we live by is not written into the bones of the universe, but woven from the threads of connection that link us all. If you trace the thread of the 2013 photon experiment backward, past the careful mirrors and detectors, past the beam splitters and the equations on the chalkboard, you arrive at something both very simple and very strange. Two things linked so deeply that the state of one cannot be described without the other. That link, quantum entanglement, is what allowed those photons to share a clock between them, to measure change in one another without an outside timeline. In a sense, entanglement is a kind of shared rhythm. Imagine two musicians who, without speaking or counting, manage to play perfectly in step. The tempo isn't being imposed from the outside, it's growing out of the connection between them. If that connection breaks, so does the rhythm. Without it, the music falls into silence, or drifts apart until there's no shared sense of before or after. In physics, without entanglement, there may be no time, at least not in the form we recognize. This is a difficult idea to absorb because we're used to thinking of time as independent of everything else. We assume it keeps moving whether we're here to watch it or not. But the Page-Wooters view, reinforced by the photon experiment, suggests something more delicate. That time may be an emergent property of how things are linked, and that without the right kind of linkage, it can fade away entirely. Where might that happen? One possibility is in extremely small systems, so small that they hold no meaningful correlations. Imagine a particle so completely alone that it has nothing to measure itself against, no partner to exchange information with. In that case, there's no internal clock to compare against the system, and from its perspective, time might simply not exist. Another possibility is in extreme environments, such as near the event horizon of a black hole. Here, the pull of gravity is so intense, and the distortions of space-time so deep, that the usual patterns of correlation may break down. Observers falling toward the horizon might still feel time passing normally for themselves, but the entanglement that links their clocks to the wider universe could stretch and twist until the outside world's concept of now no longer matches their own. And then there is the very early universe, the moment just after the Big Bang. In those first fractions of a second, the cosmos was a seething, dense quantum state, perhaps without enough structure or separation for meaningful entanglement to form. Without those correlations, there may have been no arrow of time, no before and after, only a timeless, undivided whole. Time, as we experience it, might have switched on only when the universe expanded and cooled enough for connections to take shape. It's equally intriguing to think about the opposite extreme, a state of maximum entanglement. In such a state, everything is perfectly correlated with everything else. You might imagine it as a choir in which every voice is locked so precisely with the others that there's no variation left, no note to mark a change. Paradoxically, perfect entanglement might feel like no time at all, because change requires differences, and differences require some parts of the system to drift out of sync. For us, here in the middle, time is everywhere because entanglement is everywhere. You're entangled in subtle ways with the people you speak to, the air you breathe, the ground you stand on, and the stars that heat the planet. The information your body trades with the world, through light, heat, motion, and memory, is part of the great network that keeps time moving. If those threads were cut, the clock might stop, at least from your perspective. This paints a picture of time that's almost social in nature. It's not the cold ticking of a metronome in an empty room. It's the hum of conversation in a crowded cafe, where the rhythm comes from the shared exchanges between everyone inside. Remove the people, remove the exchanges, and the cafe falls silent. Time is not just an empty background. It's something that's made together by connection and interaction. That view also shifts how we think about isolation. In deep space, far from any planets or stars, time would still tick for you because you carry entanglement within your own body. The atoms of your heart still share correlations with each other and with the environment you bring with you. But if you could strip all of that away, every link, every shared pattern, then you might find yourself in a place without moments, where nothing could be said to happen in sequence. In that sense, the experience of time might be less about clocks and more about belonging. A clock only matters because it can be read against something else. Another clock, a process, a change. Without those relationships, time loses meaning. The photons in the 2013 experiment reminded us of this. Alone, neither photon had a story to tell, but together they could write one for each other. It's humbling to think that something so central to our lives might be so dependent on something as fragile as quantum entanglement. And yet, it's also quietly beautiful. It means that time, in some sense, is woven from the same threads that connect us to one another and to the universe at large. We carry our moments with us, but we also share them, consciously or not, in every interaction we have. In the next part of our journey, we'll step from this broad view into something even more personal. The idea that you yourself are part of the clock. Not just reading it, not just carried along by it, but actually helping to make it, simply by existing in connection with the rest of the universe. And once you see yourself that way, the flow of your own moments starts to feel different, less like a river you're drifting down, and more like music you're helping to play. It's easy to imagine clocks as something separate from us. Objects on a wall, glowing numbers on a phone screen, delicate hands moving under glass. They mark the hours, we follow them. They are the keepers of time, and we are merely the audience. But if time is built from correlations, from the entanglement between systems, then the truth is far less detached. You're not just looking at the clock, you are part of it. Every beat of your heart is a tick in a network of clocks. Every breath you take changes the balance of carbon dioxide in the air around you, which in turn shifts the patterns in plants and oceans and weather. The photons that strike your eyes, carrying the image of a sunrise or a friend's face, are part of an endless chain of cause and effect, each link shaped by the state of countless other systems. You are not separate from this. You're embedded in it, woven into the same fabric that allows time to exist at all. If Page and Wootters are right, then your now is not an isolated moment sitting on some master timeline. It's a relationship, the intersection of all the changes you can observe and all the changes you're part of. You don't just move through time, you help define it for the systems entangled with you. When you speak to someone, your voice becomes part of their clock, a marker against which their own moments are measured. When you touch something, when you move through a space, when you remember, you're adding to the mesh of correlations that give the universe its sense of sequence. This isn't just poetic license. In physics, an observer isn't someone who stands outside the experiment with a notebook. It's any system that becomes correlated with another. Your body is constantly exchanging energy, momentum, and information with the world around it. In doing so, it becomes part of the entanglement structure that, in this view, makes time possible. You are both the clock and the thing the clock is measuring, and because these correlations are local, your flow of time is uniquely yours. No one else's now is exactly the same as yours. Even if you stand side by side with someone sharing the same air, the specific network of interactions you're part of will be different from theirs. In relativity, this is called the absence of a universal now. In emergent time, it's more than just geometry and gravity. It's the deeply personal nature of your connections. Think about the way a conversation unfolds. The pauses, the responses, the small shifts in tone. They form a rhythm that exists only between you and the other person. Someone listening in might hear the same words, but they wouldn't feel that exact timing, because they're not part of the exchange in the same way. In a sense, that rhythm is its own tiny version of time, born from the interaction, existing only for those inside it. Now imagine scaling that up. Not just two people, but everything you interact with. The light from a distant star that took thousands of years to reach your eyes, the gravitational pull of the moon subtly affecting the fluids in your body, the chemical signals in the food you eat that were shaped by seasons and soil and sunlight. All of it becomes part of the web of interactions that define your personal flow of time. And in return, you become part of someone else's clock. The movements you make, the heat you give off, the words you speak, ripple outward, however faintly, to change the state of other systems. You're a participant in the unfolding of their now, just as they are in yours. This way of looking at things can make time feel less like something that happens to you, and more like something you're helping to create in every moment. It's not a river carrying you downstream, it's a weaving. Countless threads meeting and parting, each crossing a small act of definition. Your life isn't just lived in time, it's part of the mechanism by which time, at least locally, exists. It also means that your memories are more than just private archives. They're records of correlations, the imprint of past interactions, and they're part of how you project time forward. When you remember, you're drawing on those stored patterns to anticipate how things will change next. In a world where time emerges from correlation, memory isn't just a byproduct of time, it's part of the machinery that makes the experience of time possible. There's something deeply grounding about this perspective. It reminds you that you're never truly isolated in the way you might sometimes feel. Even in quiet solitude, you're still connected. Through light, through air, through the echoes of every interaction you've ever had. The clock doesn't stop just because you step away from the noise. It keeps ticking in the interplay between you and the universe, in ways that might be too subtle to measure, but not too subtle to matter. And perhaps most comforting of all, it means that your now, the one you're living in this instant, is uniquely yours, and yet inseparable from the now of everything else. You're not a spectator in some cosmic theatre. You're part of the stage, part of the actors, and part of the script all at once. The story of time is not being told to you, it's being told with you. As we leave this thought behind and prepare to step into the next part of our journey, we'll start to see how this view begins to blur the boundaries of causality itself. The idea of one thing happening before another, of effects following causes. Because in some quantum systems, even that order can fade, just as surely as a universal clock can disappear. And when it does, our familiar ideas about what happens when will have to be rebuilt from the ground up. If you've ever climbed a hill and paused to catch your breath, you might have noticed that the air feels thinner, the light a little sharper, the view just slightly different from what you saw at the bottom. What's harder to notice, because it's far too subtle for our senses, is that your clock has also changed. Not the one on your wrist, but the one in your body, in your atoms, in the very rhythm that measures your moments. By standing higher, farther from the pull of the Earth's gravity, you have made your time run ever so slightly faster than it did below. Relativity has been telling us this for more than a century. Gravity doesn't just pull on space, it tugs on time. Where gravity is stronger, time slows. Where gravity is weaker, time speeds up. The effect is tiny in our daily lives, but it's real, and we've measured it with exquisite precision. Atomic clocks placed at different heights, separated by just a few centimeters, will eventually drift apart in their readings because of the difference in gravitational pull. Time, it turns out, is not immune to weight. On the grand scale, this is what lets GPS satellites guide you home with such accuracy. Orbiting high above Earth, their clocks run a little faster than those on the ground. Engineers must account for this difference, adjusting the signals so that the satellite's time and our time match. Without these tiny corrections, your navigation would wander miles off course in a single day. But relativity's story is not the only one here. At the quantum scale, gravity may be doing more than stretching or squeezing the flow of time. It might also be weaving time's very fabric by entangling the clocks themselves. This is a newer and more delicate idea, but the reasoning is quietly persuasive. If time emerges from correlations and gravity can subtly change those correlations, then gravity is not just a sculptor of time's pace, it's part of the machinery that creates it. Imagine two perfectly synchronized clocks, one on a mountaintop and one in a valley. In classical physics, their difference in tick rate comes purely from relativity. Gravity slows the lower clock, speeds the higher one. But in the quantum view, there's another layer. The gravitational field, by interacting with both clocks in slightly different ways, can create a kind of shared information between them, a gentle entanglement. This entanglement doesn't just keep time, it defines what keeping time means for those clocks in the first place. This is not the sort of entanglement you see in physics headlines, where particles seem to share an instantaneous connection across vast distances. It's quieter, more local, more like a faint harmonic resonance between instruments tuned to the same key. But even this subtle link can shift how the clocks agree on before and after. The pull of gravity, which we think of as purely physical, begins to blur into the realm of information, into the question of how reality decides what happens when. If you picture the universe as a stage, gravity doesn't just tilt the floor or stretch the curtains. It rearranges the lighting, changes the way the actors see each other, even alters the cues they use to deliver their lines. For the audience, the play still unfolds in order, but the meaning of that order is shaped by the gravitational field in ways that might only become clear if you could step outside the stage entirely. For most of us, gravity's grip on time is a quiet constant. We live within its influence so completely that it feels like the most stable thing in the world. But in physics, stability often hides complexity. The fact that you're now on the ground is not quite the same as you're now a few floors up means that time is never as universal as we might like to believe. And when we combine that insight with the quantum view, the idea that these differences might also shift the very entanglement structure that makes time possible, we start to see gravity not as an external force acting on time, but as a partner in its creation. It's worth pausing to imagine this on a personal scale. You're part of the clock, and gravity is one of the threads stitching you to every other part. The way you move, the height you stand, the planet you're on, all of it changes your relationship to time, however slightly. When you lean against a tree, you and the tree are both under the same gentle compression of Earth's pull, sharing the same slow drift of moments. Climb a little higher into the branches, and that drift changes, almost imperceptibly, but enough for physics to notice. This interplay of relativity and quantum thinking is still being explored. We don't yet have a full theory that unites them, but hints are emerging. Experiments that place delicate quantum systems in different gravitational potentials to see whether their internal sense of time shifts, not just in rate, but in structure. Each result adds another thread to the tapestry, suggesting that gravity may be one of the weavers, not just a hand tugging on the finished cloth. As we move forward, we'll explore what happens when this interplay becomes even stranger, when we change the very frame of reference from which we watch events, and the sequence itself begins to blur. But before we get there, it's worth holding on to this simple truth. Gravity's pull is not just on your body, not just on your path through space, but on your path through moments. It's part of what lets your clock, the one you are part of, keep its rhythm in the first place. In classical physics, there's a kind of comfort in knowing that the order of things is fixed. If you see lightning and then hear thunder, everyone else nearby will agree that the lightning came first and the thunder came after. Your position might change how quickly you hear the sound, but not the order itself. This is the stage that classical physics builds for us. A solid floor, a stable backdrop, a script in which the scenes always follow in the same sequence, no matter where you sit in the audience. But in the quantum world, the stage is more like a set that can be rearranged without warning. The order of scenes is no longer guaranteed to be the same for every viewer. Two observers can watch what appears to be the same play, and yet disagree about which scene came first. And in some cases, the play is written in such a way that first and second don't exist at all until someone actually looks. To understand this, we need to think about reference frames, the perspectives from which events are measured. In classical physics, switching frames can change the details, like how fast something is moving or how long it takes to get from one point to another, but it doesn't scramble the sequence of events. A runner crossing a finish line still does so after the starting gun, no matter where you watch from. In quantum physics, however, reference frames are not just about shifting your viewpoint in space and time. They are themselves quantum systems, with their own uncertainties and correlations. Changing your reference frame can mean changing the very structure of the information you have about the events you're observing. And when that happens, the order of those events can blur. Physicists call this the quantum switch, a situation where the order of two operations is not fixed, but exists in a superposition of both possibilities. It's like giving two actors the same two lines of dialogue, but letting them deliver them in either order, and somehow, in the strange logic of quantum mechanics, they manage to perform both versions at the same time. Only when you watch the recording, when you make a measurement, does one version of the sequence become the one you see. An analogy might help. Imagine two friends deciding to cook dinner together. In the usual way of things, one might chop the vegetables first and then boil the water, or vice versa. In the quantum world, until you check, it's as if both sequences are happening. The vegetables being chopped before the water boils, and the water boiling before the vegetables are chopped, both existing together in a delicate, unobserved balance. The order becomes real only when you step into the kitchen and look. Now layer gravity into this picture. If gravity can change how clocks tick, it can also change how we define a reference frame. A small shift in gravitational potential could subtly alter the way events are correlated, reshaping the stage on which those events occur. In a quantum reference frame, this means that not only can the pace of the scenes change, but their order can too. The very structure of cause and effect starts to feel less like a rigid line, and more like a flexible braid, strands weaving over and under each other until the measurement pins them in place. This doesn't mean that in your everyday life you'll suddenly experience your morning coffee before you grind the beans. At the scale of people and planets, the classical order of things holds firm. But deep down, in the fine threads of reality, there are places where before and after are not absolute truths, but provisional agreements, waiting to be settled by observation. This is one of the reasons physicists are so interested in experiments that combine quantum systems with gravitational effects. By creating conditions where the reference frame itself is quantum and influenced by gravity, they can probe how flexible time's ordering really is. Could there be situations where even space-time itself doesn't insist on a single sequence? Could the flow of moments, at its most fundamental level, be more like a cloud that can be shaped from different angles, rather than a river that flows one way no matter what? If the answer is yes, it would mean that our everyday experience of cause and effect is like one version of the play, the one our particular seat in the theatre happens to show us. Someone in another seat under slightly different conditions might watch the same story unfold with a different rhythm, a different ordering of events, and still be equally correct. And if you could somehow see the play from outside the theatre entirely, you might discover that all possible orderings coexist, waiting for a perspective to bring one of them into focus. It's a strange way to think about reality, that the stage itself can be rewritten simply by shifting your point of view. But it's also a reminder that time, as we know it, is not necessarily the fixed, universal background we often assume. It may be something more relational, more dependent on the interplay of perspective and connection. In our next step, we'll take this idea to its most extreme test, the edge of a black hole, where gravity stretches time to its breaking point, and where the quantum and relativistic pictures of time collide in ways that force us to question whether inside and outside can even agree on what now means. If you could drift toward a black hole, not fall suddenly, but approach slowly, as if walking toward the edge of a cliff you can't quite see, you would find the flow of your moments changing in ways that feel impossible anywhere else. From far away, your friends watching you would see your movements slow, your gestures stretching out, your words drawing longer and longer until they become inaudible. You would appear to them as if you were moving through honey that gets thicker with each step, and eventually you would seem to freeze entirely, held in place just outside the black hole's boundary, the event horizon. From your perspective, nothing so dramatic would happen. Your heartbeat would keep its rhythm, your breathing would stay even, your thoughts would move from one to the next in the same gentle pace they always have. You would cross the horizon without feeling any sudden change. Inside, time would go on flowing for you, for a while. The paradox is that both views are correct, even though they cannot be reconciled. Outside and inside no longer agree on what now means, and the gap between those definitions widens with every passing moment. This is relativity's most extreme demonstration, the way gravity stretches time. Near the event horizon, the stretching becomes so intense that it approaches infinity for an outside observer. But when we bring quantum physics into this picture, the strangeness deepens. If time emerges from correlations, and those correlations depend on both entanglement and gravitational effects, then the very boundary of a black hole might be a place where our definitions of time collapse altogether. Consider the light and matter falling in. Each particle carries information about its energy, its spin, its quantum state. And in falling toward the horizon, it becomes entangled with the rest of the universe in ways that are hard to fully track. Some of that entanglement is stretched to near breaking by gravity. Some may be cut off entirely when the particle crosses the horizon. If the Page-Wooters picture holds true, then from the outside, this severing of correlations might mean the internal time of those particles no longer exists in any way that can be meaningfully compared to our own. From inside, though, time continues. The falling particle, or you if you're the unlucky traveller, still experiences change. But those changes are sealed off from the outside world, as if you've stepped into a separate story with its own clock, one that no longer shares a common beat with the universe beyond. The result is a kind of temporal fracture. The universe is still one thing, but its pieces are no longer stitched together by a single timeline. Each region keeps its own rhythm, and in the case of a black hole, those rhythms might be so out of step that they can't be reconciled at all. The event horizon is not just a spatial boundary, it's a divide between different realities of time. Physicists still don't fully understand what happens here. The equations of general relativity work perfectly well outside the horizon. The rules of quantum mechanics work perfectly well for particles on their own. But when we try to apply both at once, to describe the fate of quantum information in the curved space-time around a black hole, we find contradictions. The order of events inside may be meaningless outside, and the smooth fabric of time we rely on in daily life may simply unravel. Some theories suggest that the horizon itself might act like a kind of hologram, storing a record of everything that has fallen in, though in a form we don't yet know how to decode. Others imagine that space-time near the horizon could behave like a tangled web of quantum reference frames, each with its own ordering of events, none of them universally right. In either case, the familiar comfort of a single shared timeline disappears. It's worth remembering that black holes are not rare, exotic things hidden far beyond our reach. They are scattered throughout galaxies, the quiet remnants of collapsed stars, and at the hearts of galaxies they grow to monstrous sizes, shaping the motion of millions of suns. They are part of the same universe we inhabit, and yet at their boundaries they show us a truth about time that feels alien to everything we experience on Earth. If the flow of moments can fracture this completely, if now can split into definitions that no longer overlap, then perhaps our everyday sense of time's unity is only a local truth, held together by the gentle conditions of our surroundings. Far from black holes, the differences are so small that we can pretend they don't exist. But at the edge of one, that pretense collapses. The stage doesn't just change its scenery, it tears in two, leaving actors and audience on separate sides of a divide they can never cross again. And yet, there is something quietly reassuring here. Even in this extreme place, from your own perspective, time remains steady. You would still feel the tick of your moments, the sequence of your thoughts, the warmth of your memories. In the end, perhaps that is what time really is. Not the universal agreement we imagine, but the persistence of change within our own frame of existence. Next, we'll step away from the black hole's edge and take a breath. The picture we've built so far of time as emergent from entanglement, shaped by gravity and sometimes fractured by perspective, will now begin to shift again, as we explore how these ideas ripple into the nature of causality itself. What happens when the order of cause and effect becomes as uncertain as time itself? In the rhythm of daily life, cause and effect feel as solid as the ground beneath your feet. You turn the key and the door opens, you switch on the kettle and the water heats. There's a comfort in knowing that one thing follows another, that before and after line up in a neat, dependable chain. This order gives the world a sense of coherence, a framework for memory, planning, and meaning. Physics, at least the kind we use to navigate trains and teacups, agrees with this structure. It tells us that causes must come before their effects, and that no amount of creative rearranging will make your coffee brew before the water boils. The arrow of time, tied to the increase of entropy, marches on in one direction, pulling causes and effects along with it like beads on a string. But as we have already seen with time itself, what feels absolute can dissolve when we look closely enough. At the quantum level, where particles behave less like solid beads and more like possibilities waiting to be chosen, even the order of events can lose its rigidity. There are experiments, delicate, almost storybook in their setup, where the sequence of this happened, then that happened, doesn't exist until we check. One such setup is the quantum delayed choice experiment, inspired by ideas from John Wheeler. Imagine you have a photon, a particle of light, and you send it toward a device that can measure it in one of two ways. The choice of how you measure it can be made after the photon has already entered the apparatus. In the classical world, this would be too late to matter. The photon's behavior would already be decided. But in the quantum world, the result you get depends on the measurement you choose, even if you make that choice after the photon's journey has begun. It's as if the effect, your choice of measurement, reaches back to influence the cause, the photon's earlier behavior. Even more striking are experiments that place two operations in a quantum superposition, a state where both possible orders exist at the same time. This is sometimes called an indefinite causal order, and it's as disorienting as it sounds. You might have process A happen before process B and process B happen before process A, both at once, with the outcome depending on the interference between these two possibilities. Only when you measure do you collapse this superposition into a single order. Until then, the chain of before and after is not just fragile, it's undefined. These aren't just curiosities. They force us to rethink what causality really is. If the order of events can depend on how we choose to observe them, then cause and effect are not as fundamental as we thought. They might be more like the storyline of a play that can be shuffled and rearranged without changing the actors' lines. The coherence comes from the relationships between the scenes, not from their absolute order in time. In our everyday lives, the world is messy enough without having to wonder whether breakfast or lunch comes first. At human scales, the quantum indeterminacy washes out and the familiar chain holds. But the fact that it can slip, even in controlled experiments, tells us something profound. The arrow of cause and effect might be a large-scale illusion, emerging from deeper, more flexible rules that don't care about order in the way we do. It's tempting to imagine this as a kind of time travel, the effect reaching back to touch its cause. But that's not quite right. It's not about rewriting the past. It's about the past and the future being less separate than we assume. At the quantum level, they can blend into a structure where before and after are just two of many possible ways to arrange events, and nature hasn't yet committed to one. This fragility of causal order is easier to picture if you think of weaving. Normally, the threads go over and under in a fixed sequence, and the pattern depends on that order. But in the quantum loom, the threads can hover in a state of over and under and over at the same time, with the final pattern only fixed when you decide to look. The design doesn't exist in a single, locked form until it's observed, and until then its possible forms overlap like faint, transparent layers. The implications are as philosophical as they are scientific. If cause and effect can be placed in a superposition, then the relationship between events is not fixed in the deep structure of reality. It might be something that crystallizes only when the conditions are right, when the right observers, systems, or interactions bring it into focus. Just as time itself may be an emergent property of entanglement, so too causality may be something that is built, not given. And if that is the case, then our sense of a sturdy, unbreakable chain linking every before to its after is really the story our corner of the universe happens to tell under the conditions we live in other parts of the cosmos, or in the earliest, moments after the Big Bang when the fabric of space-time was still raw and unsettled. That story might be entirely different. In the next session we'll step fully into that idea, that causality itself may not be fundamental, but a product of how the universe knits its information together. And if so, then our familiar cause and effect might be just one arrangement among many, one way the threads can be woven in the vast, quiet loom of reality. It is comforting to think of causality as a built-in feature of the universe, something etched into its foundations from the very first moment. We imagine the cosmos as having started with a kind of master blueprint, a sequence of events stretching forward from a beginning, each cause leading inevitably to its effect, all the way to the present and beyond. But if we take seriously what quantum physics is whispering to us, that even the order of events can slip into ambiguity, then this comforting picture might not be the whole story. Instead, causality may be less like the walls of a house, and more like the patterns in frost on a window pane, something that forms under the right conditions, beautiful and intricate but not inevitable. It is an arrangement that emerges from the way the pieces of the universe connect to each other, from the correlations that link one part of reality to another. Without those connections, or with different ones, the pattern could be entirely different. The analogy to time here is strong. Earlier, we explored the idea that time itself may emerge from quantum entanglement, from the way a clock system and a rest of the universe system share information. In the same way, causality might emerge from the way information flows between systems. If those flows are stable and directional, we experience a clear arrow from cause to effect. If they are unstable, reversible or tangled, that arrow can blur or even vanish. Physicists sometimes describe this in terms of causal structures, frameworks that map out how information can travel from one event to another. In a well-behaved classical world, these structures look like branching trees. Each event leads to others, and you can trace a path backward to see what caused what. But in more exotic quantum situations, those trees can loop back on themselves, merge in unexpected ways, or fail to have a clear route. It's as if the branches don't know which way they're supposed to grow. This doesn't mean that the world descends into chaos. Even in such strange conditions, there can be internal consistency. The system can still follow its own rules. It just doesn't have to match our everyday expectation that A must precede B. Causality, in this sense, is something that can be locally built out of the available correlations, like a temporary bridge assembled from whatever materials are on hand. In one place, the bridge runs from left to right. In another, it runs in the opposite direction. In some rare places, it might run both ways at once. This perspective can be unsettling because it moves causality from the category of absolute truths into the category of emergent behaviours. And emergent behaviours, by their nature, can change. They can be absent in some conditions, altered in others, and only stable in a narrow range of circumstances. Our familiar one-directional cause and effect might be a special case, a fortunate alignment of factors in our region of space-time. It is worth picturing this through something familiar. Imagine a village built along a river. The river flows steadily in one direction, carrying goods from upstream farms to downstream markets. The whole life of the village, its work, its trade, its rhythm, depends on that direction. Now imagine that, for reasons no one can quite explain, the river sometimes reverses or splits into two channels flowing in opposite directions. The villagers would have to change how they work, adjusting their expectations and plans each time. In a similar way, if causality can be shaped by the conditions of the universe, then different regions of reality might have entirely different cause and effect arrangements. From a scientific standpoint, the idea of built causality suggests that we should look for the physical principles that give rise to it. These might involve the density and type of entanglement between parts of a system, the geometry of space-time itself, or the constraints imposed by energy and information flow. Causality could be the outcome of a balancing act between these factors, just as frost patterns are shaped by temperature, humidity, and surface texture. And just as frost can form in endlessly varied shapes, causality might have many possible forms. Ours happens to be linear and mostly irreversible, giving rise to the familiar comfort of before and after. But in other environments, perhaps near black holes, in the early universe, or in engineered quantum systems, it could take on forms we find alien. Philosophically, this leads to a subtle but powerful shift. If causality is built, not given, then our sense of history, of one moment flowing from another, is a product of the particular web of correlations we inhabit. This doesn't make it any less real for us, but it does mean it is not the only way reality can be arranged. The chain of events that defines your life is a local construction, not a universal law written in the bedrock of existence. And there is something quietly humbling in that. We live inside a story that our corner of the universe tells well, a story where each scene follows from the one before, where consequences make sense, where plans are possible. But out beyond the edges of that comfort zone, there may be places where the story is told differently, or not told at all, and perhaps, if the conditions are right, causality could dissolve entirely, leaving only a web of relationships, without a clear before or after. Next, we will step into one of the strangest expressions of this idea, quantum states that hold multiple causal orders at once, like rivers flowing in opposite directions, but meeting in the same ocean. In these superposed timelines, the rules of cause and effect are not just rewritten, They coexist in incompatible versions until the moment we choose to look. Standing on the bank of a wide river, the water moves past you in a steady direction, carrying leaves, twigs, and the occasional ripple from a distant splash. Now imagine that the river is joined by another, flowing in exactly the opposite direction. Not in a chaotic whirlpool, but in a strange, seamless coexistence. If you stood there long enough, you might see a leaf floating downstream pass right beside another leaf gliding upstream, each following its own current as if the other did not exist. Both flows are real, but they do not share the same definition of forward. This is the kind of paradox that quantum physics makes possible. In certain carefully prepared quantum states, the order of events is not fixed and not merely unknown. It is genuinely in a superposition of different orders. Event A happens before event B, and event B happens before event A, both at once, like those two rivers flowing toward opposite horizons. Only when you look, only when a measurement forces the system into a definite history, does the river choose a single direction. One of the most striking realizations here is that the concept of before and after in these cases isn't something that's hiding from us, waiting to be revealed. It doesn't exist until the act of observation creates it. This is not ignorance, it is absence. The system is not secretly following one order or the other. It is following both, or perhaps neither, until the conditions change. Physicists have built experimental versions of this idea using the so-called quantum switch, where two operations are placed in a superposition of different orders. For example, you might have a particle that can travel through two devices, A and B, which each change the particle in some way. Classically, you would send the particle through A first and then B, or through B first and then A, and you would get two different outcomes. But in the quantum switch, the order is put into superposition, and the particle experiences both sequences at the same time. The final state of the particle contains the signature of this indefinite order, a kind of interference pattern in the fabric of cause and effect. It's tempting to picture this like a story where the ending changes depending on the order in which the chapters are read. Except in the quantum case, the book is somehow being read in both sequences simultaneously, and the meaning of the story is woven from the interference between those readings. There is no true sequence until the reader, the measurement, fixes it. What's especially curious is that this superposition of orders might have practical uses. In some situations, performing two tasks in an indefinite order can yield better results than doing them in any fixed sequence. This isn't just a curiosity, it's a resource, a way of harnessing the flexibility of causality for computation, communication, or other quantum technologies. It's as if the river flowing both ways could carry goods more efficiently than a river locked into a single direction. From the perspective of emergent time and causality, superposed timelines are a kind of extreme case, a place where the local rules have not yet crystallized into a single, ordered flow. If time emerges from correlations, and causality emerges from the structure of those correlations, then a superposition of orders is like a universe caught mid-weave, where the threads haven't decided which way to run. There is something almost poetic about this. We think of our lives as single threads, running in one direction, past events trailing behind and future events waiting ahead. But in the quantum picture, there can be places where threads run both forward and backward at once, touching the same points from opposite directions. They meet, they cross, they vanish into the same knot, and only when we lean in close do we see the direction settle. It's natural to wonder whether this means time could ever run backward for us, whether we might someday watch an effect undo itself into its cause. The reality is less cinematic. The superposition of orders doesn't let us rewrite history in the dramatic science fiction sense. Instead, it shows that the relationship between events is not always bound to a single path. It's not so much about travelling upstream as it is about discovering that upstream and downstream can be defined in more than one way, and sometimes both ways at once. Still, the philosophical weight of this is hard to ignore. Our entire sense of narrative, the way we remember, plan, and act, depends on the idea that events come in a single, fixed order. If that order is something the universe can treat as optional, then the story we live in may be just one draft among many. The superposed timelines in quantum experiments might be fleeting and fragile, but they are real, and they are telling us something. That the linearity we trust is not the only mode of existence reality can take. In the sessions ahead, we'll begin to step back from the quantum laboratory and look at how all of these ideas, emergent time, shifting reference frames, fractured timelines, and superposed causal orders, might connect into a broader picture of reality. But for now, hold on to the image of the two rivers meeting in the same ocean, their waters mingling without ever agreeing which one came first. In that quiet confluence, there is a hint of how flexible the deep structure of time and causality might truly be. If entropy is the spreading of possibilities, entanglement is the deepening of connections. One works in the space of arrangements, how many ways the pieces can be placed. The other works in the space of relationships, how tightly and intricately those pieces are bound together in ways you cannot see by looking at them alone. Both move in the same direction, though they take different paths to get there. Imagine a pair of coins on a table. If you flip them separately, the results are independent. Knowing one is heads tells you nothing about the other. Now imagine that the flips are somehow linked so that whenever one is heads, the other is always tails and vice versa. This link is not a visible chain, it's a hidden rule. You can look at either coin in isolation and see randomness, but together you find a pattern. That invisible binding is a crude analogy for quantum entanglement, the correlation between systems that cannot be explained by local, separate properties. In the quantum world, entanglement grows naturally as systems interact. Particles scatter off one another, exchange energy, and become subtly connected, carrying information about each other in ways that persist no matter how far apart they drift. These connections don't fade with distance, only with disturbance, with the intrusion of outside noise that disrupts the delicate quantum state. Over time, in almost any real setting, the network of entanglement tends to thicken, spreading like roots through soil. Here's where it begins to rhyme with entropy. Just as entropy measures the number of possible arrangements, there is a related quantity called entanglement entropy, a way of describing how much quantum correlation exists between a part of a system and the rest. In many systems, as time passes, entanglement entropy grows. It's not just that the parts become more disordered in the classical sense, they also become more woven together in the quantum sense. This growth might be telling us something profound about the arrow of time. If time emerges from correlations, as the Page-Wooters view suggests, then the steady thickening of these quantum connections is the same motion we experience as forward. Entropy increases because the system explores more configurations. Entanglement increases because those configurations are linked by deeper and deeper webs of correlation. Both are different faces of the same unfolding. There is an everyday metaphor hiding here in the kitchen. Think of making soup. At first, the ingredients are separate. The carrots here, the onions there, the broth clear. As the soup simmers, the flavours spread, blending into one another. You can no longer scoop out the onion flavour from the carrot flavour. They're bound together in a way that wasn't there before. The mixture has more arrangements because the molecules have spread, and it has more entanglement because the parts now carry information about one another that didn't exist at the start. Physicists see this process in systems as small as a few particles and as large as entire galaxies. The same mathematics that describes the increase of entropy often also describes the growth of entanglement. In some cases, the two can even be plotted side by side, showing parallel climbs over time. It is as though the world is walking on two paths at once, each step adding both to the number of possibilities and to the depth of connection. And perhaps this is why the arrow of time feels so consistent. We're not just moving into states with more disorder, We're also moving into states where everything is more entangled with everything else. That means the past is a place with fewer connections, simpler, more separable, while the future is a place where separation becomes harder and hard to find. It is not just that the cup breaks, it is that the pieces learn something about one another in breaking, an unspoken memory of the shattering that can't be undone without erasing the connections entirely. In a sense, entropy and entanglement are the outward and inward expansions of the same process. Entropy is the blooming of possibilities in the space we can see and measure. Entanglement is the knitting together of possibilities in the hidden quantum layer beneath. Both have the same consequence. They make it impossible to return exactly to where we were. You could, in principle, reverse every motion and every interaction, but you would also have to unweave every quantum thread, an act so complex that it becomes effectively impossible. The more we look at the universe through this lens, the more it seems that time's arrow is not a single arrow at all, but a braid. One strand is thermodynamic entropy. Another is quantum entanglement. They run side by side, twisting around each other, sometimes inseparable, sometimes distinguishable, always pointing in the same direction. And just like a braid, their strength comes from their intertwining. Pull one strand out entirely, and the structure begins to fall apart. In the next session, we'll look at those rare moments when this braid seems to loosen, when scientists find ways to reverse, at least partially, the evolution of a quantum system. These tiny reversals are not time travel, not even close, but they offer a glimpse into what it means to tug gently against the current, if only for a moment, before the river resumes its steady flow. In the everyday world, there is no going back. Once the glass has shattered, its edges lie fixed in their new shapes, and the floor remembers the sound of its breaking. The coffee cools, the ink spreads, the river carries its water onward without pause. The arrow of time, guided by entropy and entanglement, keeps its steady direction. And yet, in certain small and carefully arranged corners of the quantum world, scientists have found ways to nudge that arrow, not to reverse its full flight, but to make it tremble, to let it sway briefly in the other direction before resuming its forward course. These moments are known as time reversals or Loschmidt echoes, and they are as delicate as they are fleeting. The principle is simple to state. If you could know every detail of a system, the positions and momenta of every particle, the exact pattern of every correlation, you could, in theory, run the equations of motion backward, step by step, and arrive at where you started. But in practice, the tiniest imperfection spoils the attempt. A grain of dust, a stray photon, a microscopic ripple of heat, all can nudge the system off its perfect reverse path, and the larger the system, the more inevitable these disturbances become. Still, in controlled laboratory setups, the reverse can be attempted. One example comes from nuclear magnetic resonance experiments, where the spins of atomic nuclei can be carefully aligned, disturbed, and then coaxed back toward their starting configuration. The process is a bit like setting a row of dominoes falling, then somehow flicking them all in just the right way to stand them back up again. When it works, the pattern of alignment reappears, a ghostly return of order from the brink of complete disorder. Another striking demonstration came from a team of physicists in 2019, using a quantum computer to manipulate the state of a few qubits, the quantum equivalent of bits in an ordinary computer. By applying a sequence of operations that mimicked the forward evolution of the qubits, and then a carefully calculated set of reverse operations, they managed to return the system to an earlier state. The result was like rewinding a tiny film of reality for a fraction of a second. It was not a leap into the past in any cinematic sense. Nothing else in the universe joined in the reversal. But within that miniature quantum island, the arrow of time bent back. These reversals are possible because quantum systems, when small and isolated enough, can be controlled with extraordinary precision. The fewer the moving parts, the easier it is to track and reverse every interaction. But this also explains why such reversals cannot be scaled up. The moment the system touches the wider world, the moment it entangles with air molecules, photons, or the warmth of a hand, the number of variables to control explodes beyond hope. The rest of the universe refuses to cooperate in running backward, and the little pocket of reversal is swept into the forward flow. This limitation is not just a practical obstacle. It is part of the deeper structure of reality. Entropy and entanglement grow because the universe is vast and interconnected, and because disturbances, once they spread, cannot be undone without affecting everything else they have touched. A large-scale reversal would mean undoing the dance of countless particles across the cosmos, each step retraced in perfect synchrony. The odds are not merely long, they are functionally impossible. And yet, these small reversals are valuable. They are not loopholes in the laws of physics, but confirmations of them. They show us that the forward march of time is not magic, not a rule carved in stone by an unseen hand, but a consequence of complexity, probability, and connection. In principle, the equations that govern motion are reversible. In practice, the world is too entangled to unweave. It is worth pausing on the image of a Loschmidt echo. Imagine a note played on a piano. The sound swells, vibrates, and fades into the air. A reversal would be like pulling every vibration back into the strings, gathering every wisp of sound from the room and returning it perfectly in phase to the moment the hammer struck the keys. For an instant, you would hear the note again exactly as it was, as if no time had passed. Then, inevitably, the sound would scatter again into the air, and the arrow would tilt forward once more. There is a quiet poetry in these fleeting backward steps. They remind us that the present is not a one-way surface, but a point balance between possibilities. The forward direction is overwhelmingly favoured, but not absolutely enforced, and in those rare, carefully crafted circumstances, we can feel, if only for a heartbeat, the strange sensation of walking upstream against the river of time. In the next part, we will leave these controlled reversals and return to the broader question. What happens when time, causality, and entropy are all woven together into the local personal experience of now? How do these vast and abstract processes converge into the simple, intimate flow you feel each moment? That will lead us into the tapestry of time as we live it, thread by thread. The world you know feels continuous. You can walk across a room, pour water into a glass, or watch a cloud drift across the sky, and there is never a sense of the world flickering or skipping. Space seems smooth, and time flows without gaps. But deep beneath this familiar surface, at scales so small they are beyond imagining, physics hints that the smoothness may be an illusion, and that time, like the ticking of a clock, could be built from intervals so brief they cannot be divided further. This realm is called the Planck scale, a domain where our usual ideas of space and time falter. The Planck length, about 1.6 times 10 to the negative 35th power 10 to the negative 35th power times 1.6 times 10 to the negative 35th power meters, is so small that if you magnified a proton to the size of the known universe, the Planck length would still be far smaller than a single atom in that universe-sized proton. The Planck time, the time it takes light to cross a Planck length, is equally unfathomable. About 5.4 times 10 to the negative 44 power, 10 to the negative 44th power, 5.4 times 10 to the negative 44 seconds. At such scales, space and time may no longer be the unbroken fabric we're used to, but something grainy, discrete, a mosaic made of tiny, indivisible units. If this is true, then time as we know it, flowing smoothly, carrying moments into one another, is a large-scale effect, like the way a movie appears fluid even though it is made of separate frames. The frames at the Planck scale might be so small and fast that we can never perceive them individually, but the analogy is incomplete. In a film, the frames are laid out in a definite sequence. At the Planck scale, we, may not even be able to speak of before and after in the way we understand them. The very order of frames might be meaningless, replaced by something more abstract, a network of relationships from which time emerges only when viewed from far away. Some theories of quantum gravity, which seek to merge general relativity with quantum mechanics, suggest that space-time itself is not fundamental. Loop quantum gravity imagines space as woven from finite loops, like a fabric whose threads are closed circles. In such a picture, time is not a river that carries things along, but a pattern that emerges from the way the loops interact and change. String theory, another contender, often treats time as just one coordinate among many in a multidimensional landscape, one that may dissolve entirely at the smallest scales. It is difficult to picture a world without time, because even the act of imagining unfolds in time for us. We think of one thing, then the next, measuring the distance between thoughts with an inner sense of now and later. But physics invites us to step outside that reflex for a moment and consider that at the deepest level there may be no river of time to flow in, only a static landscape of possibilities. Our experience of movement and change could be the result of tracing a path through this landscape, as if consciousness were a traveller moving from one point to another, not because the points themselves change, but because the traveller does. If space-time is discrete, then there is a smallest possible step between one state and another. Below that, the concept of passing from one moment to the next might not exist. This would mean that asking what happened between these two moments could be as meaningless as asking what is between the rungs of a ladder. There is simply empty space, or perhaps not even that. And yet, even if time vanishes at the Planck scale, it can still reappear at larger scales, much as temperature appears when many molecules move together, even though no single molecule has a temperature. The smooth, unbroken time of our everyday life might be a statistical effect, the average behaviour of countless discrete events blending into one continuous flow. In this way, time could be like music heard from far away. The individual notes blur into a sustained tone, but the tone exists only because the notes are there. This idea is both unsettling and oddly comforting. It means that the solidity of time, the way we live in it, rely on it, and measure our lives by it, is not something guaranteed by the universe's deepest laws. It is a gift of scale, a pattern that emerges only when enough of reality is woven together. Beneath that weave, the threads may not run in any order at all. In the next session, we'll move from the smallest imaginable scales to the largest, to a time before time, when the universe itself may have existed in a state without moments, without sequence, and without change, until the first connections formed and the first arrow of before and after appeared. We are used to the idea that everything has a beginning. A journey begins with the first step, a book begins with its first page, a life begins with its first breath. It is natural to imagine the universe in the same way, as something that started perhaps with a great burst of light and energy, and then unfolded moment by moment into the world we know. The Big Bang is often pictured this way, an explosion in space and time, a point from which everything rushed outward. But physics asks us to consider something stranger. What if, in the earliest state of the universe, there was no earliest at all? What if there was no time in which the Big Bang could happen? In many cosmological models, the beginning of the universe is not a moment in time, but a transition from a state without time to a state with time. Imagine a perfectly still ocean stretching endlessly in every direction. Nothing moves, nothing changes, nothing happens. Without change, there is no way to tell whether time is passing or not, and in a real sense, it is not. Now imagine that, for reasons we do not yet understand, tiny ripples begin to form on the surface. The ripples interact, merge, and grow, and suddenly the ocean is alive with patterns. Only then could an observer inside that ocean begin to measure before and after, marking time by the motion of the waves. The early universe may have been like that still ocean, a timeless state where space, energy, and even the seeds of matter existed, but without the correlations needed for time to emerge. In the Page-Wooters picture we explored earlier, time is a product of relationships between systems. If nothing in the primordial state could serve as a clock for anything else, there would be no ticking, no arrow, no unfolding. Some versions of quantum cosmology describe the universe's earlier stage as a kind of frozen hole, all possible configurations existing together without sequence. The equations that describe it, like the Wheeler-DeWitt equation, have no explicit time variable at all. They treat the cosmos not as something evolving in time, but as something existing timelessly, with history being a concept that applies only after certain structures form. In such models, the Big Bang is not a bang at all, but the moment when the first correlations became strong enough to define a direction for change. This is not an idea meant to be grasped all at once because our own minds are steeped in time. Even to imagine before time forces us to cheat, to smuggle in some hidden sequence. First there was timelessness, and then time began. But in truth, without time, there is no then to follow the first. The transition might not be something that happened. It might simply be the difference between two ways of describing the same reality, one without clocks, one with them. We can turn to a gentler image. Think of a book written in invisible ink. To the eye, it appears as a blank page. There are no words, no sentences, no sense of order. But under the right light, the writing appears, and with it comes the story, the sequence of events. The invisible ink was there all along. The words only needed the right conditions to reveal themselves. In this way, the timeless universe might have held within it the potential for time all along, waiting for the right conditions, the right correlations to bring the story into view. Cosmic inflation, the rapid expansion that is thought to have shaped the early universe, may have been part of this awakening. As space expanded, tiny quantum fluctuations were stretched and amplified, becoming the seeds of galaxies, stars, and planets. These fluctuations also created a kind of cosmic clockwork, giving structure to the universe in a way that allowed time to be measured. Before that expansion, it may have been impossible to speak of one event happening after another. And what of the moment we call the Big Bang? It may be less the starting gun of a race, and more the lighting of a lamp in a dark room. The lamp does not create the room, it reveals it. The Big Bang in this picture is not when the universe began to exist, but when it began to tell time. The philosophical weight of this is hard to ignore. If there was a state of timelessness before our familiar universe, it changes how we think about origins. We cannot ask what happened before, because the question is built on an assumption that may not apply. There may be no before to speak of, only a timeless expanse out of which our moving, changing, living cosmos crystallized. In the next session, we will turn from this distant past to the far future, asking whether time could ever end again, whether the universe might return in some ultimate quiet to a state without clocks, without change, and without the steady beat of now and later. We often imagine the end of time as something abrupt, a final cataclysm, a clock that stops ticking all at once, leaving only silence. But physics paints a subtler possibility. Time might not end with a crash. It could fade slowly and imperceptibly until it is no longer there to be counted. The river might not hit a wall, it might simply become still water, without current or direction. One vision of this future comes from the idea of the heat death of the universe. In this scenario, the cosmos continues expanding for unimaginable lengths of time. Stars burn out, galaxies grow dark, and the last flickers of starlight fade into the black. Eventually, all matter is scattered so thinly, and all energy is spread so evenly, that there are no differences left for anything to change. Without change, there is nothing to mark one moment from the next. Time's arrow, which depends on the increase of entropy, reaches its destination, maximum entropy, where no further growth is possible. In such a state, nothing happens, not because motion is forbidden, but because there is no meaningful difference between one configuration and another. Every place, every moment, every particle becomes indistinguishable from every other. It is the cosmic equivalent of silence so deep that it erases even the memory of sound. From the perspective of quantum physics, a similar stillness could arrive if the universe reached maximum entanglement. As we've seen, entanglement grows as systems interact, weaving a web of correlations between them. But if every part of the universe became maximally entangled with every other part, there would be no new connections to make. All possible correlations would already exist. Without the possibility of creating new patterns, the network of relationships that gives rise to time in the Page-Wooters sense could stop evolving. It is an eerie thought. Time not as a thing that gets switched off, but as a property that quietly evaporates because there is nothing left for it to measure. If change is the ticking of the cosmic clock, then in this future, the clock still exists, but its hands are frozen, not because they are stuck, but because there is nothing left to move them. To picture this, imagine a library filled with every possible book. At first, you can spend lifetimes moving from one story to another, finding new plots and new characters. But once you have read them all, every new book you open is one you have already read. Turning the pages no longer changes what you know. The sequence of reading becomes meaningless. The library is still there. The books are still there. But the experience of time, the movement from one new thing to the next, has vanished. Of course, such a future lies far beyond anything we can truly picture, trillions upon trillions of years past our current age, and the laws that might govern it are still uncertain. The universe may not head toward heat death at all. It could instead collapse in a big crunch, tear itself apart in a big rip, or undergo strange phase transitions that create new arrows of time. But the possibility that time itself could lose meaning remains one of the most haunting. It suggests that the arrow of time is not eternal, but a temporary feature of a changing universe, a phase that began when the first structures formed and will end when structure itself dissolves. This idea changes the way we think about forever. We tend to picture forever as an infinite stretch of moments, one after another without end. But if time can fade, then forever might be something else entirely. Not an endless series, but a single, unchanging state. A stillness so complete that before and after are meaningless words. If the universe does end in such a stillness, it might be in some ways like the state that preceded time at the very beginning, a return to a timeless expanse. In that sense, the story of time would be like a breath, drawn in, held and released. Time would begin, expand and then disappear, leaving behind only the quiet from which it came, and here perhaps is the most unexpected comfort. In such a view, the time we live in is precious precisely because it is temporary. It is a rare season in the universe's history, the season when things change, when patterns form and dissolve, when memories can be made. We exist during the part of the story when the pages are still turning. That makes each moment, however small, part of a fleeting miracle. In the next part, we will step away from the extremes, the smallest scales and the largest spans, and return to the human scale, to the woven fabric of now, as it exists in our own lives. We will see how the grand theories and far futures connect to the way you feel, time passing in your own heartbeat, your own breath, and your own memory. If you set aside all the distant galaxies, the black holes, the quantum fields, and the hypothetical timeless states, you are still left with something remarkable. You are a living measure of time. Even without watches, calendars, or the movement of the sun, your body quietly keeps track of passing moments. and it does so in ways that are both mechanical and poetic, because you are not just a clock, you are also a listener, tuned to rhythms that began long before you were born. Your heartbeat is the most obvious rhythm, pulsing steadily through your chest. Each beat marks a small moment, not in numbers or minutes, but in the language of your body. The rise and fall of pressure, the gentle push of blood through arteries. This rhythm changes with your state. It slows when you rest, quickens when you run, and dances in subtle ways when you feel fear, joy, or anticipation. Though it is measured in beats per minute, it is also a kind of music, one that plays whether or not you are aware of it. Then there is your breath, another clock of the body. Inhale, exhale, inhale again. Like the ticking of a pendulum, it swings between two states, pulling oxygen in, sending carbon dioxide out. You can control it for a while, speeding it up, slowing it down, even pausing it, but eventually it returns to its own rhythm, a reminder that the body has its own sense of time, separate from the one in your mind. There are slower rhythms too, hidden beneath daily awareness. Your body temperature rises and falls over the course of the day, following a cycle tied to your internal circadian clock. Hormones surge and ebb in patterns that repeat every 24 hours, influencing your alertness, mood, and even how your memory works. Every cell in your body contains its own molecular timekeepers, tiny biochemical loops that help coordinate your activities with the day-night cycle of the world outside. These rhythms are not just internal, they are also responsive. Your body listens to cues from the environment, light, temperature, sounds, and social patterns, and adjusts its timing accordingly. When morning light reaches your eyes, it tells your brain to shift into a waking state. When darkness falls, it signals the release of melatonin, nudging you toward rest. Even the timing of your meals, conversations, and movements plays a role in synchronizing your inner clocks. This listening goes beyond biology. You are sensitive to the subtle patterns of the world around you, the way a room feels different at dawn than at dusk, the pace of footsteps in a quiet street versus a crowded market, the long pause between waves at the shore. These are not just background details, they are temporal markers, shaping your perception of how fast or slow life is moving. In this way, your experience of time is as much about receiving as it is about counting. It's worth noting that your body's clocks do not always agree with one another. Jet lag, for example, is the feeling of your various internal rhythms falling out of sync. Your sleep cycle disagrees with your digestion, your temperature cycle, and your alertness patterns. Part of what makes the feeling so strange is that you are, in a sense, made of many different clocks, and when they disagree, you feel the dissonance. On the smallest scales, your cells are constantly measuring and responding to time without your awareness. DNA is copied, repaired, and expressed according to precise schedules. Proteins are built, modified, and recycled in cycles measured in minutes or hours. Neurons fire in patterns that can encode memories in fractions of a second. And even these cellular events are themselves influenced by the grander cycles of the body, which are in turn tuned to the cycles of the Earth, the Moon, and the Sun. Seen from this perspective, your body is not just living in time, it is a layered network of timekeepers, each playing its own part in a larger symphony. Some keep a steady beat, like the percussion section in an orchestra. Others swell and fade like strings or horns. The result is the particular flow of now that you experience, one that is unique to you, shaped by your biology, your surroundings, and your history. And perhaps most beautifully, your body does not only measure its own time, it also synchronizes with others. Conversations have their own pacing, with pauses and responses that align in ways neither person consciously plans. Walking beside someone, your steps often fall into the same rhythm without effort. In music, dance, or shared work, people align their movements and breathing almost automatically, creating a shared sense of time that feels as natural as it is unspoken. You're not just a clock in isolation. You're part of a network of clocks, linked by signals both visible and invisible, adjusting and readjusting to stay in tune with the living world. It is an intricate, ongoing negotiation, one that happens without you having to think about it, yet shapes the tempo of your entire life. In the next session, we'll step deeper into this personal side of time, exploring how the present moment, the now, is not a sharp instant, but a soft, overlapping span that gathers together your past, your present, and even a little of your future into a single living experience. If you try to point to the present moment, to catch it like a pebble in your hand, you quickly find it slipping away. The instant you name it, it has already passed. And yet the now you live in is not razor thin. It is soft at the edges, a gentle overlap of what has just happened, what is happening, and what is about to happen. Your mind stitches these together so smoothly that you experience them as a single flowing moment. This blend is not an illusion, it is a necessity. The brain takes time to process information from your senses, light striking your eyes, sound reaching your ears, touch against your skin. Each signal moves along nerves at finite speeds, is interpreted by layers of neurons, and only then becomes part of your conscious awareness. That means your present is actually a collection of events that occurred milliseconds ago, assembled into a coherent scene. Neuroscientists sometimes call this the specious present, the short span of time your brain treats as now. It may last only a few seconds, yet within it are dozens of micro moments, layered and blended. When you hear a melody, for example, the note you're listening to is intertwined with the echo of the one before it, and the anticipation of the next. The song would not make sense if you could only hear a single note in isolation. This weaving of moments also explains why you can catch a ball, dance to music, or speak in conversation without constant surprise at what's happening next. Your brain is always predicting what is about to occur based on patterns you've experienced before. These predictions are not separate from the present, they're part of it. Your now is not just a record of what has happened, but also a sketch of what is likely to happen next, constantly updated as reality unfolds. There is a quiet comfort in knowing that your mind is not simply a passive receiver of time, but an active shaper of it. The world comes to you as a stream of impressions, but you decide, without realizing it, where the edges of your moment are drawn. In some situations, that moment feels long and expansive, as in a slow evening walk when the air is cool and unhurried. In others, it feels sharp and fleeting, as when you react instinctively to catch a falling glass. The shape of now changes with your state of mind, your body, and your surroundings. Memory plays a role here too. The edges of the present reach backward, pulling in fragments of the recent past to give context to what you're experiencing. If someone calls your name in a crowd, you may realize you had already heard their footsteps approaching seconds before. These small memories are stitched invisibly into the present so that your actions can make sense. Without them, life would feel disjointed, each moment arriving without connection to the last. At the same time, the present leans forward into the immediate future. If you watch a friend raise a glass to drink, you're already preparing for the moment their voice will pause in conversation. If you walk along a path, you adjust your stride for the curve you see ahead. This anticipation is so natural that you rarely notice it happening. It is as if part of you is already living a second or two ahead of your body, smoothing the path before you arrive. From a physics perspective, this subjective now has no universal counterpart. Relativity tells us that different observers, moving at different speeds or sitting in different gravitational fields, will disagree on which events happen at the same time. There is no single cosmic present that all beings share, and yet in your personal experience the present is deeply real, an anchor in a universe that offers no fixed centre of time. It is here, in this space between memory and anticipation, that your life unfolds. The richness of your experience depends not only on the quantity of moments you live, but on the quality of this overlapping present. Some moments are dense with detail, carrying the smell of rain, the sound of footsteps, the warmth of a hand in yours. Others are light and sparse, passing almost without notice. Time's flow is shaped less by the ticking of a clock than by how fully you inhabit these moments as they pass. And there is a softness to this realization. You are never entirely in the past or the future. You are always in a layered now, a space that holds echoes, possibilities, and the touch of reality all at once. You cannot freeze it, but you can learn to notice it, to feel its texture. In doing so, you may find that time seems to slow, not because the seconds are changing, but because you are paying attention to how they gather. In the next session, we will step into the final chapter of this journey to see how the story of time, from quantum entanglement to the far future, finds its quiet rest in the way you carry these moments with you, even when your eyes are closing and the world is fading towards sleep. You have travelled a long way tonight, not in miles, but in moments. We began at the edges of physics, where time itself can flicker, stretch, or dissolve, and we have slowly walked back here to the quiet space where your own breath marks the passing of the present. Along the way, we've seen time as a web of correlations, a tapestry of rhythms, a river with many branches, and sometimes no river at all. We have looked at it through the eyes of Einstein, through the logic of quantum mechanics, through the stillness of the early universe, and the imagined hush of its far future. And now, we stand not at an end, but in the soft middle of things, because every end is just another point in the flow. The seconds keep folding into each other, and the stories they hold keep unfolding, whether you watch them closely or let them pass quietly in the background. Time is not a thing you can hold. It will not sit still for you to examine. It is more like the warmth of sunlight on your skin. You feel it without catching it, and it fades even as you notice it, and yet it leaves something with you. A memory, a trace, a shape in the way you think and feel. Every moment, no matter how fleeting, becomes part of the path that leads here to this one. In the vastness of the universe, the kind of time you know, the kind that can be marked by heartbeats, by laughter, by the rise and fall of days, may be rare. We live in a season when change is still possible, when patterns still form and dissolve. Before this, there may have been only stillness. After this, there may be stillness again. But right now, there is movement, and you are within it. Perhaps that is the most extraordinary thing about time. It is not something separate from you. You're not simply moving through it. You're part of how it is made. Your memories are threads in its fabric. Your choices shape its direction, in ways both small and immeasurable. Even your act of noticing, of sitting here, listening, breathing, is part of the universe's way of telling time. Think of how a river sounds at night. You cannot see the water, but you hear it moving, carrying with it pieces of places you have never been. Each drop passes only once, yet the sound is constant, and the river as a whole feels eternal. In the same way, you may not feel each second distinctly, but they carry you forward, their quiet motion shaping the world around you. And like a river, time has many branches. Somewhere else, someone is looking at the same moon you could see if you stepped outside, though for them, it may be a different phase, a different hour. For someone moving faster, or sitting in a different pull of gravity, the flow is not quite the same. And yet, to each of you, it feels natural, personal, your own stretch of the river. The story of time is not complete, and perhaps it never will be. Our theories may grow, our understanding may shift, and the language we use to describe it may change entirely, but in some ways that is fitting. Time itself does not reveal all its patterns at once. It shows them gradually, moment by moment, like stars appearing in the evening sky. So as you lie here, perhaps with your eyes closing, you can let the ideas drift the way leaves drift downstream, not needing to follow each one, not needing to hold them in order. They will still be here in the morning, or in whatever moment you choose to return. The heartbeat you hear now is not the same as the one before it. The breath you take now is not the same as the last. Yet they are connected, part of the same gentle story, part of the same quiet clock. The light that touches your skin, the memories that float through your thoughts, the warmth you feel, all of it is the sound of time moving softly around you and within you. And as this journey into the nature of time comes to a close, there is nothing you need to solve, no conclusion you need to reach. You can simply rest here, in the overlap of what has been and what will be, knowing that the present moment will carry you forward without you having to do anything at all. Time will keep its watch, and you can let go. Sleep well, little story of time. The universe will keep turning its pages while you dream,